see my screen now?
Yeah. Yes. Yes.
Okay. Hello everyone. I'm Rosalia a track trainee in the second year now, and I'll be presenting to you on how to choose a correct type of regression analysis. So basically, I'll concentrate on the GLMs, generalized linear models, and yeah, that's what I'm going to concentrate on today. Here are the contents of my presentation. So I started introducing the GLMs, then going to the linear regression model, which is the background or the backbone of all of the GLMs, and then the assumptions of the GLMs, and then into the logistic and the count data models. So first, regression analysis mathematically describes just the relationship between a set of independent and dependent variables. Then there are numerous of regression models that you can use, and I'm not going to really cover all of them. We really have so many regression models. And this choice is often depending on the type of the dependent variable. So explaining dependent and independent variables. Dependent variables is like the outcome variable, like when you're trying to show a relationship between maybe mortality and some predictors. So the dependent variable would be the mortality, and the predictors like age, sex, or a certain exposure like a medicine would be the independent variable. So that's it, to explain the difference between the independent and independent variables. So when you're trying to choose actually which model you will use, we concentrate on the dependent variable. And actually, not only that, but we'll also look at the type of model that provides the best fit. So we'll concentrate on most common types of regression analysis and how to decide which one is right for your data. Sorry. Covering regression models that are appropriate for dependent variables that will measure either continuous, categorical, and count data. So continuous variables, these are variables that assume an infinite number or real values within given interval. For instance, consider the height of a person or a student or the age. And categorical variables are also qualitative variables. They are also known as qualitative variables. This refers to those that cannot be quantifiable. Categorical variables can either be nominal, example, those which follow natural order, do not follow any natural order, like just sex, either male, female, or ordinal, good, very good, excellent. There's a level within this, but sorry, you can't quantify it actually. So, and the count data are observation recording the number of units at a given time that failed or were lost because of censoring. So failed here in count data is having the outcome of interest, and censoring are those that get out of the follow, they're no longer in the follow-up, but have not experienced the outcome of interest. So this is to explain the three types of dependent variables that we are going to concentrate on today. So concentrate on dependent variables that are continuous, dependent variables that are categorical, and dependent variables that are count data. So going into GLMs, GLMs is an extension of linear regression models. Linear regression models which allow for other distributions. So linear regression model itself, it's like in the history back then, it was the only model that was available to use. And it has some restrictions because of its assumptions. So a linear regression model requires a normal distribution. So the generalized linear models allow or it is flexible for other distributions. It allows other distributions other than the normal distribution of the outcome. And this uses a link function. So here, I'm not going to get into very details of this, but the components of generalized linear models includes a response distribution, which means that it assumes responses are identical independent distribution. And sorry, this is IIDs, identical independent distribution. And it follows a statistical distribution from exponential family. As I say, it allows other distributions apart from the normal distribution. And it also uses a link function. The link function relates the outcome mean to a suitable quantity for the model. And also uses a linear predictor, which is a linear combination of explanatory variables that are used to predict the link function. And assumptions for GLM actually there are assumptions that are specific for each type of GLM, but I'm trying to just put them all together. Those are the important assumptions. So we have, for each regression model, a different statistical distribution is assumed for the random errors. So the random errors for normal distribution in linear regression, and random error are binomial distribution for logistic regression, and Poisson distribution for exponential or Poisson regression. So you see here the three different distributions for the three different models. And also individual observation are independent. That means that the probability of one event occurring in one observation is not really dependent in any way in a probability of the event occurring in another. So they are independent. There's no correlation in the observations. And linear relationship between the outcome and explanatory, this is mainly for the linear regression. And variation of observation is constant over predictors. Variance of observation is constant over predictors. This means that the effect of the outcome on the predictors is the same for all levels of the predictor. And the last assumption is that random errors are independent of predictors. Going into the first model that I said, the ones that have a dependent variables as a continuous variable, the linear regression model. This uses ordinal least squares and linear least squares. This is the real workhorse of the regression world, because I think it's the one that started. There are no any other models. Right now we have even machine learning models. There are so many models right now, but this one was the first one. And it used ordinal least squares it gives the mean change in a dependent variable given one unit change in each independent variable. This analysis estimates parameters by minimizing the sum of squares, the sum of square errors. We can see from this graph that for every unit change in the exposure, there's a change in the outcome, but the observations are really scattered. So the regression line is produced by the process of ordinal least squares and by minimizing the sum of squares. You can see in the linear regression, the observations in red are assumed to be the results of random deviations. In green, the green are the random deviations from underlying relationship, which is the blue, between a dependent variable y and the independent variable x. So the lines are really trying to minimize the errors and producing one fit line. So the advanced types of linear regression, because not all assumptions are really met for all data types that require linear regression. So we have issues like outliers, multicollinearity, and it is prone also to overfitting. So an outlier is a single data point that goes far outside the average value of a group of statistics. I wish I had a diagram here, sorry. And multicollinearity is a statistical phenomenon that occurs when two or more independent variables in a regression model are highly correlated with each other. In other words, multicollinearity indicates a strong linear relationship among the predictors. So if this happens, you really have to, there's a way to work it out, but there are other options you can use if that happens. Overfitting also can happen, and this mostly is in machine learning, where it occurs when machine learning models give accurate predictions for training data, but not for the new data. There are reasons why that occurs. And examples of advanced type of linear regressions, they're like lasso, ridge, partial least squares. I'm not really good in those models, but just an example of them. Yeah. So regression analysis with categorical dependent variables. So we have seen analysis where the dependent variable is continuous. Now we're going into the regression analysis with categorical dependent variables. A categorical variable has values that you can put into a countable number of distinct groups based on their characteristics. So the first one is logistic regression. And basically, the dependent variable here is categorical. And it uses maximum likelihood estimation rather than the least squares to estimate parameters like we saw in the linear regression. Logistic regression describes the relationship between a set of independent variables and the categorical variables. Choosing this type of logistic model is based on the type of categorical dependent variable you have. So there are also different types of categorical variables that would also make you choose a certain type of model in the logistic family. So we have binary logistic regression. Here we use a binary logistic regression to understand how changes in the dependent variables are associated with change in the probability of an event to occur. This type of model requires a binary dependent variable. It has to be binary, meaning that it has only two possibilities, either fail or pass, or other examples are like the disease presence, maybe the disease is there or not, mortality has occurred or not. So it only, the dependent variables has only two options, which is either it has occurred or not. So that's a binary logistic regression. So coming to ordinal logistic regression, this model is chosen when the predictors, when there's a set of predictors and an ordinal response variable meaning the dependent variable. So the dependent variable here has at least three groups which have natural order, such as, there's a natural order such as hot, medium, or cold. You see there are levels there. Other examples are like socioeconomic status, low income, middle income, high income, education level, high school, bachelor's, master's, PhD, income level less than. So you see there are levels within these independent variables. Then in this case, the ordinal logistic regression is appropriate to use. Nominal logistic regression also is another option in the logistic family. And here the dependent variable is, it has at least three groups which do not have any natural order. We saw the other one that had natural orders, but here there is no any natural orders. And it is also called multinomial logistic regression models. An example of these variables that, dependent variables that are nominal could be genotype, the blood type A, B, or B, zip code, gender, race, eye color, political family. Those are examples of nominal logistic of dependent variables that would require nominal logistic regression. So that was a dependent variable that has a categorical manner. Now we're going into the count data. So regression analysis with count data. First, count data frequently follow the Poisson distribution. We earlier saw that there are three types of distributions within these models that we are discussing today. The normal distribution, the binomial distribution, and the Poisson distribution. Now we're from the binomial distribution, and now we are into the Poisson distribution. A Poisson distribution is a discrete probability distribution. It gives the probability of an event happening a certain number of times within a given interval of time or space. So the Poisson distribution has only one parameter, lambda, which is the mean number of events. A classic example of Poisson data is provided in the Ladler's, I don't know how to pronounce this, but Kiwis, a Russian economist who analyzed annual death caused by horse kicks in the Prussian army from 1875 to 1894. So you see, the counts here were the number of deaths, and the number of deaths were being followed up within this time range, and that makes a count data. So we use Poisson regression to model how changes in the independent variables are associated with the changes in the counts. Poisson model are similar to logistic model because they use maximum likelihood estimation, as we said. and transform the dependent variable using a natural log. This time we are using a natural log. Poisson model can be suitable for rate data, where the rate is a count of events divided by a measure of that unit exposure, a consistent unit of observation. For example, homicides per month, or we saw the other example that mortality per that time range. So the assumptions with the Poisson regression is that there should be account data, and the distribution of the dependent variable should be Poisson distribution. The events should be occurring at random in the Poisson distribution, and events are independent. And the most important one, or the one that distinguishes it, is the constant baseline hazards. Constant baseline hazard means that the hazard ratio for any two individuals in a population is constant over all times. We can see from the graph here that the outcome is the hazards for the outcome is the same throughout the throughout the follow-up time, but this is for the baseline. For the baseline, yeah, baseline meaning that without considering the effect of the exposure. So without considering the effect of the exposure, the hazard rates are constant over time. That is the assumption for Poisson. Now, the problem, if that is the case with the data, with your data, after looking at the assumption, after testing for the assumptions, and you find that there's a constant baseline hazards, then it's okay. But most of the time, that is not the case. And not all data also follow Poisson distribution. So fortunately, there are alternatives you can perform when you have count data. So we have negative binomial regression, zero inflated models, and others we'll see on as we move on. But I'm not going to talk a lot about this, but the negative binomial regression model, these are Poisson regression models that assume that the variance equals the mean. When the variance is greater than the mean, your model has over dispersion. A negative binomial model, also known as NB2, is can be more appropriate when over dispersion is present. And for zero inflated models, the zero inflated models, your count data might have too many zeros to follow the Poisson distribution. In other words, there are more zeros than Poisson regression predicts. So there the zero inflated models would be appropriate. So Poisson model after lexics expansion. So we said that not all data would really have a constant baseline hazards. So relaxing that assumption, we can do a Lexis expansion. A Lexis expansion is trying to split the times into different levels, so as to have the constant baseline hazards only within those splitted times. So maybe you can split using age or calendar time. So this would actually relax the assumption. And rate will be allowed only to change within the bands, the time bands. So another way, we can move to COGS. Moving to COGS when Lexis expansion has not worked, after very, very fine Lexis expansion. So rates can change continuously. We allow rates to change continuously, but the rates are allowed to change proportionally. So introducing the proportional hazards assumptions. Cox regression does not calculate baseline rates in this case. We already said that the baseline are meant to be constant. Now we are trying to relax this assumption by allowing it to change proportionally with the exposure. And we really cannot talk about the baseline hazards here. So rates can vary over time, not constant. Uses risk sets to estimate hazard ratio at each time point. We can see from the diagrams. Here is where I was talking about the Cox regression, relaxing the assumption of baseline hazards into proportional hazards, and using the Lexis expansion here, the time is splitted into different bands and allowed to vary within the bands. But with the Cox regression model, we see that the baseline hazards are allowed to vary, but they have to be proportional with the exposure. Yeah, the same down here. So if that isn't the case, we have to do something about it. But how will we know that the proportional hazards assumption is not met? So we can do a visual assessment using the log-log plots. We can try to see the goodness of fit. This is a post-estimation command using the Schoenfeld residuals. And we can also do modeling time-based interactions. Modeling and interaction with time, follow-up time into the Cox model. So these are three ways in which we can know if really the assumption of proportional hazards is met so as to use the Cox regression model. So we see here the log-log plots. The first diagrams show the assumption is met. These two lines are really parallel. They're not intersecting in any way. And this second diagram shows an intersection. So if this happens, then the assumption is violated. So what happens if the assumption is violated? We can first use a stratified Cox, but a stratified Cox means using the variable that has violated the proportional hazards assumption and stratify it you stratify using that variable to get the estimates. But this isn't really reliable when that variable that has violated the assumption is your primary exposure. So that is the disadvantage, and so we can use then an extended Cox model. This model is utilized when primary exposure has violated proportional hazard assumption. We must see its direction effect on the outcome. And you can see it's stratified on time, the extended Cox stratified on time. Like the less than 1 year, greater than 1 year, just to get away with the place where the two lines have intersect, to have a proportional hazards in at least one of the bands. Yeah. So I think, yeah, that's all for today. I know there are a lot of things that I was not able to cover, but yeah, concerning GLMs and what is really considered in selecting a model. Thank you.
Thank you, Rosalia. Thank you for this overview of the different families of GLMs. I think this is very important because in the end, the decision is always a little determinant on the data, but you kind of guide us through what they meant. There's some assumptions in the discussion there that we assume people, but it might make sense for us to at some point discuss what is the difference between using a maximum likelihood approach versus using an OLS approach, and what is the differences between them. What is an over dispersion, and why does that affect a Poisson distribution? But we can discuss that on other days. Did you follow a paper or our guidance, or did you build this based on some other sources?
Yeah, I have references here, but I
Okay.
also used some documents that were shared with us with our professors at the college. So I had different sources here.
Okay. Yeah. No, I'm just curious if there's a good paper we could keep as a source for this discussion that we could use to build a document out of this.
Not really one paper that has all of them in one place. No, not really.
Okay.
Yeah.
All right. Yeah, I also don't recall stumbling upon one, but if anybody has a good paper that kind of gives an overview of the different GLM methods, would be good to have it as a document. Okay, sounds good. So Nathan, can you ask Natalie if she would be willing to show us codes to fit each one of these models? She should have them readily and easily from the labs that we were giving this past semester. So it should be pretty straightforward for her to show the difference between just how you fit these models using R.
Yeah, I'll check with her, see if she has availability to do it.
Cool. That would be good. Okay. All right. Thank you, Rosalia. What do we have lined up for next week?
Yeah, thank you for the opportunity.
Thank you.
The learning process, yeah.
You're always welcome.
Asante.
Joel Victor, can you show the spreadsheet? I don't think I can share my screen.
Yes, I can. Sorry. Here. Can you see my screen?
Yeah.
Or actually,
Yeah.
which screen are you seeing?
It's
The
right
spreadsheet.
Okay.
Yeah. Okay,
Cool.
so for next week, we have Igor presenting cluster analysis.
Okay. Is that confirmed?
I'll confirm this today to make sure it's going to be.
Nathan, do you have Igor's contact information?
I think so. I'll check it.
If you don't, let me know. I have his WhatsApp. Let's see if he's
Okay.
available. If he's not, I can bump my presentation on his spot if he's not ready. If that's the case.
Okay, sounds perfect. I think I have his contact, and try to reach out to him. If I don't, then I text you to see if you can contact him. Thank you so much.
Sure. About the João, you were talking about the Natalie coming up with the template codes as well. We
Yeah.
had a few folks lined up for doing those templates for some of those topics. Do you want to engage them together?
Are these templates for codes or for writing?
We just discussed. We brainstormed of having these templates, but I don't remember if they were supposed to be for codes or just writing.
Yeah, I think I would rather have them. I'd love to have both of them, that we had a good marker on how to report. So if we could use those days to, instead of having a presentation, having a discussion around a template for writing and a template for codes, that would be great if people are up for it.
Okay. We have here Rosalia, who just presented to us on the general for the GLM models. So Rosalia, are you still planning on working on this one for binomial regression? Okay, I see you nodding your head. Thank you.
Okay.
Yeah, sorry, I was muted. Yeah.
Don't worry.
As I said, we have pretty good codes for each one of them. So happy to share those resources for whoever's working on it. And that would be good. So instead of spending time preparing a slide, just prepare a template on how you would write the methods and the results for this particular method. And then a piece of codes. And it doesn't have to be refined in the meeting. We can come to the meeting together and talk it through and then refine it together.
Sounds good.
Okay.
Yeah, so just before we just change the subject a little bit, I am lined up to present next. One of the next topics is on that Gemini package that I talked to some of you. But I'm also signed up on the general Gemini meeting next week. Let's see if it's next week. I guess it is.
It
On the
is.
3rd of June. So
Yeah.
what I'm thinking is that if Igor is not available next week, it's going to be a double, it's going to duplicate the presentation. But then on this call, we can focus on how did I work through developing the package, what I thought about it, like how does it work. Whereas on the Gemini meeting, I can just show like why we should use it, how it's helpful, like a high level description.
Yeah. That's what I think. Here we can go in more detail, João. We can even go in more detail on potential edits we want to make or changes and decisions you made on how you're reporting some of these pieces.
Okay, we can even do like take one of our data sets and see how it looks.
Cool. That would be good. Yeah. Okay.
Nice.
All right. So then for the folks preparing documentation, the GLMs, what we're talking about is having a Google Doc that functions as a template. And on the Google Doc, you should have a method section on how you would describe the results or the method approach for that particular GLM approach. And then on the results part, you would have how you would report that with a table shell and suggested figures that we would like to show. And then we're going to have the codes. And then I think it's going to be a good exercise. We're going to iterate that a few meetings until we get something mature. But that would be an interesting exercise. If you're working on this and you can share it, great. If not, we can talk it through during the meeting. And then we can discuss based on people's experience, how they see these results reported and how we can find ways to report it. That would be good.
Yeah. This is just a small example. So this is for a template for the KTS calculation that we did. So this is something that you could use to describe on your methods how it was calculated.
Yeah.
And-
Open the one for meta-analysis, João.
Okay.
I think that's the last one that I created.
Maybe it's this one.
Yeah. So here you have a plug and play for what you would write in the methods. And I was doing that on GitLabs at the time, but we can probably just keep it on a Google Doc, and then João and I can, or someone else can put on GitLabs again on the Gemini GitHub this time. But then it also has the structure for the results as well. So this is literally something you would copy and paste on your study, and then you would change the areas that are under brackets to whatever is from the study at hand. And that would give you something that we know has good quality. Okay, that's where we want to get at. Cool. Okay. All right. Thanks again, Rosalia. We'll end a few minutes early today. We'll see you again next week. Bye.